Hello everyone. Welcome to the next lecture on the linear algebra. Today I will explain you what are the various properties of the eigenvalues, and each property I will explain you with the help of the numerical examples. Myself Dr. Harish Garg, you can follow and subscribe my YouTube channel. Now what we have discussed so far, we have learned the concept of the eigenvalue and the eigenvector. If you have any matrix A, definitely it is of the square matrix, then you can define the eigenvalue as the root of the characteristics equation. If I called the equation number 1 is called as characteristics equation, then the roots of this polynomial or roots of this equation is known as eigenvalue. This eigenvalue is also known as the characteristics roots or called as the latent root. Second concept is what is the meaning of the eigenvector? We can find a non-zero vector x. Remember, always there is always a non-zero vector x, such that the equation ax is equal to lambda x satisfied. Then you can say the non-zero vector x is said to be eigenvector. For more detail about the concept, about the geometry of the eigenvalues and the physical significance, you can watch about my playlist linear algebra, and you can see the lecture of linear of the eigenvalue and the eigenvectors. Here you can learn the concept of the physical significance and the geometrical properties of the eigenvalues. Also remember, the eigenvector is also known as the latent vectors and so on. Now let's start with the various properties of the eigenvalue and the eigenvector. So before I start with the first property, I hope you can like and comment on the video. The first property is the sum of the eigenvalue. If you have the matrix A, then for example, if I say my matrix is 1, 2, 3 and 4, then definitely, since it is a 2 cross 2 matrix, so how many eigenvalues are there? There are the two eigenvalues, lambda 1 and lambda 2. The first property say the sum of the eigenvalue is the trace of the matrix. What is the meaning of the trace? That means the sum of the diagonal entries. The sum of the diagonal entries. So in this example, what is the diagonal entries? 1 and 4. So that means lambda 1 plus lambda 2 is my 5. Second property says the product of the eigenvalues is the determinant of the matrix. So can you find the determinant of the matrix? That is my 4 minus 6, which is minus of 2. Fine. That is the meaning of this first property. The proof is very simple. If I consider that any n cross n matrix, fine, then we can define the characteristics polynomial a minus lambda I. That will be a11 minus lambda, a12 and up to a1n, then a21, a22 minus lambda up to a of 2n and so on. The last row will be an1, an2 and the last element will be ann minus lambda. Fine. Now if you expand this, how you can find it? That will be a11 minus lambda into the other minus. Fine. Similarly second component and so on. But if you try to expand it, what will happen? You can try to write in terms of the coefficient of. So you can see lambda is a negative. That will be minus 1 raised to power n. Similarly, the next term will be minus 1 raised to power n minus 1, lambda of n minus 1 into a11 plus a22 and so on. Now, if I substitute the value of lambda is equal to 0 in equation number 1, what will happen on the left hand side? That is my determinant of A. This quantity will be 0. This quantity will be 0 and so on. The only term which is left behind is the constant terms of the determinant A minus lambda I. Fine. Now, how you can find the constant terms? So if I say lambda 1, lambda 2, lambda n are the roots of the polynomial, then what is the meaning of the roots? That means I can write this equation is lambda minus lambda 1, lambda minus lambda 2 and up to lambda minus lambda n. Fine, because it has a negative. Fine, so I can write as. Now if you open this bracket, what will happen? First, if you open this complete bracket, is a lambda raised to power n, then minus 1 raised to power n, or you can say negative sum of the coefficient lambda of n minus 1 and so on. Now you can compare the equation number 1 and equation number 2. Left hand side are same. The first quantity, which is my same, coefficient of the lambda raised to power n minus 1. If you open this bracket, it is same. So that means a11, a22, a of n, which is equal to lambda 1 plus lambda 2 and lambda n. And the constant term is my a determinant, and the constant term is lambda 1, lambda 2. Why? Because if you multiply this value with the minus 1, so it becomes minus 1 raised to power 2n, which is always 1. So what you observe, that means the sum of the eigenvalues is the trace of the matrix, product of the eigenvalues, this is the product, is the determinant of the matrix. Look at the examples. If I consider the example, how you can find the sum of the eigenvalues. So I will tell you the two different methods. First method is by using the property. First method I will tell you by using property, and second method I will tell you by using the calculation. Fine. Calculation means by the definition. So what is the first properties? By using the property of first property, sum of the eigenvalue is trace of the matrix. Can you find the trace of the matrix? 2 plus 3. The 5 is the right answer of the problem. Second method is, if I start with the characteristics polynomial, a minus lambda I is 0. Fine. A minus lambda I, that is a 2 minus lambda, 3 minus lambda, and it is 1 and 1. Fine. This equation is known as characteristics equation. So can you find the determinant? 2 minus lambda, 3 minus lambda, minus of 1 is equal to 0. If you open this bracket, it is lambda square plus, minus 5 lambda, fine, plus 6 minus 1 is equal to 0. That implies lambda square minus 5 lambda plus 5 is equal to 0. So can you factor them? So that will be lambda is equal to minus b plus minus b square minus 4ac divided by 2. So which implies 5 plus minus root 5 divided by 2 are the eigens value of this matrix A. So therefore, what is the sum of the eigenvalues? The first eigenvalue is 5 plus root 5 over 2. Second eigenvalue is 5 minus root 5 over 2. So you can add them. The sum will be 10 over 2, that is a 5, which is similar to the first method of the eigenvalue. Second example is, for the matrix A, find the product of the eigenvalues. Again, I will tell you the two methods. First method is by using the property. Second method is by using the definition. So what is the product of the eigenvalues? If there are the 2 cross 2 matrix, there are the two eigenvalues. The product of the eigenvalue is nothing but my determinant of the matrix. So can you find the determinant of the matrix? 12 minus 2, which is the 10, is the right answer of the problem. Always remember, the first method is very useful once you are entering the CSR net, GATE, IIT JAM, or any of the competition examinations. By using the second methods, how you can do that? I can write the characteristics equation a minus lambda I, which is 0. So that implies 4 minus lambda, 3 minus lambda, 1 and 2 is equal to 0. Now can you expand this determinant? So that will be 4 minus lambda, 3 minus lambda, minus of 2 is equal to 0. Now if you open this bracket, it is lambda square minus plus 12 plus minus of 2. So can you factor them? It will be lambda minus 5, lambda minus 2. So therefore, eigenvalues are my 2 and 5 are the eigens value of the matrix A. Fine. And now your target is to find the product of the matrix. So product of the eigenvalue. So what is the product of the eigenvalue? 5 into 2. That is my 10. And you can see both the answers are same. Similarly, in this case, if somebody will ask you, find the sum of the eigenvalues. Fine. So what is the sum of the eigenvalue is 7. And again, you can see 5 plus 2 is 7 is again the same answer. Second property, the square matrix A and A transpose. For example, if my A is 1, 2, 3, 4 or 5, 6, 7, 8, 9. Fine. And what is the A transpose? A transpose will be 1, 2, 5, 3, 4, 6, 7, 8, 9. If I say lambda 1, lambda 2 and lambda 3 are the eigenvalues of the A, then A transpose has also the same eigenvalues lambda 1, lambda 2 and lambda 3. Fine. Now the proof is a very simple. What the meaning of the eigenvalues A? If I assume lambda is the eigens value of the matrix A, what does it mean? That means determinant of the A minus lambda I is 0, or you can say A minus lambda I of x is my 0. Clear? Now since my target is to start from the determinant, so let's start with the determinant. If I write this determinant, how you can write that? It's A transpose minus lambda of I transpose. What is the I transpose is? I transpose is always I. Fine. Because my target is to start from the transpose, so I can start with the transpose. Now let's start with the A minus lambda I of transpose. Now taking, you can say, taking the determinants on the both side. Fine. Taking the determinant of the both side, so you will get A transpose minus lambda I. Fine. And we all knows for any matrix, say H is any matrix, determinant of the H matrix and determinant of the H are same, where H is any matrix. Fine. So for this case, I can say A minus lambda I, which is same as A transpose minus lambda I. Clear? Now, because lambda is the eigenvalue of the A, therefore determinant of A minus lambda I is 0. Now, if I say the left hand side is 0, so I can say A minus lambda I is 0 if and only if A transpose minus lambda is 0. Fine. What does it mean? This implies lambda is the eigenvalue of the A, and by using the definitions, lambda is the eigenvalues of the A transpose. Why? Because whenever you can write A minus lambda I is 0, that means lambda is the eigenvalue of the matrix A. And if you look about that, lambda is the eigenvalue of the A transpose, lambda is the eigenvalue of the A. That implies lambda is the eigenvalue of the A if and only if lambda is the eigenvalue of the A transpose. Look at the numerical example. If I say the matrix A has the eigenvalue 2 and 5, can you find the eigenvalues to A transpose? Again, I will tell you the two different methods. First method is by using the property. Second is by using the definitions. Now, because A and A transpose has the same eigenvalue, therefore A transpose has also 5 and 2 are the eigenvalue. Second method is we can calculate it. Firstly, what is the A transpose? A transpose will be 4, 2, 1 and 3. Fine. Then you can write the characteristics equation. A transpose minus lambda I is equal to 0, which implies 4 minus lambda, 1, 2, 3 minus lambda is equal to 0. Now, can you expand them? If I open this bracket, it's a 12. Find the determinants. It's a 12 minus 7 lambda plus minus of 2 is equal to 0. That implies lambda square minus 7 lambda plus 10 is equal to 0. Now you can easily factor them. it will be 2 and 5 are the eigens values of, I can start with the A transpose, which is the A transpose. And now you can see A has the eigenvalue 2 and 5. Lambda A transpose has also the eigenvalue 2 and 5. Okay, can you find the eigenvalues of the A transpose? If 2, 2, 3 are the eigenvalues of this matrix, can you find the eigenvalue of the A transpose? Now because A and A transpose has the same eigenvalue, therefore 2, 2 and 3 are also the same eigenvalue. You can also check your answer in the examinations. You can see what is the trace, what is the sum of the eigenvalue. What is the sum of the eigenvalue? So 2 plus 2 plus 3, fine, 7. And then what is the trace of the matrix? You can also see trace of the matrix is also 7, which are same. So by the first property, you can also verify that. Moreover, you can also verify that the product of the eigenvalue is, you can see 2 into 2 into 3, fine. And if you find the determinant of the matrix A, you will again get answer is 12. Okay, look at the next properties. Before I can explain you that these two properties, I hope you can like and comment on the videos. Okay, if lambda is the eigenvalue of the A, so if the A has eigenvalue lambda, how you can find the A inverse eigenvalue? That will be 1 over lambda. So that is very simple. So if I start with them, lambda is the eigenvalues of the A. What does it implies? That means A minus lambda I of x will be 0, or if you open this bracket, it is Ax is equal to lambda x. Fine. Now we need the A inverse. So how you can do that? So I can multiply both side by A inverse. So I can pre-multiply both side by A inverse. The left hand side becomes A inverse of Ax. The right hand side becomes A inverse of lambda x. The A inverse of A will be I. Lambda is a real, so that will be the outside. A inverse of x. Fine. So that I can say what is the value of the A inverse of x, because lambda is a real number. Fine. Or you can say lambda is a scalar value. So I can divide them 1 over lambda into x. Fine. Now from this equation 1, what is that? If, what does it implies? That means lambda is the eigenvalue of the A. Now you can see 1 over lambda is the eigenvalue of the A inverse, because it's again look like say Ax is equal to lambda x. Hence 1 over lambda is the eigenvalue of A inverse. Similarly, the next property is if lambda is the eigenvalue of the orthogonal matrix. Orthogonal means A into A transpose is identity, or you can say A inverse. If you multiply both sides by A inverse, you will get here. If lambda is the, you can see if lambda is the eigenvalues of the A, and by using the previous property, because we need a transpose, that means lambda is the eigenvalue of the A inverse or A transpose, because A and A transpose are same. Now lambda is the eigenvalue of, because A transpose is my A inverse. Fine. So that means, and what is the value of the A inverse? The eigenvalue of the A inverse is 1 over lambda. If lambda is the eigenvalue of the A, 1 over lambda is the eigenvalue of the A inverse. Fine. If A inverse is equal to A transpose, so that means 1 over lambda is also the eigenvalue of the A transpose, and eigenvalue of the A and A transpose are same. Therefore, 1 over lambda is also the eigenvalues of the A. Now look at this example. Find the eigenvalues of the A inverse. So look at that. A has 3 cross 3 matrix. So it has 3 eigenvalues. Definitely A inverse has also 3 eigenvalues. The 2 eigenvalues we have known, 2 and 8. The third eigenvalue is unknown to us. So can you find the eigenvalue of the A inverse? So if lambda, if 2 is the eigenvalue, 1 over 2 is the eigenvalue of the A inverse. 1 over 8 and 1 over lambda 3. So it means our target is to find the value of the lambda 3 only. Fine. So how you can find that? It's a very simple. I can assume that lambda 3 is the third eigenvalues of the matrix A. Fine. Now we can use the first property. Sum of the eigenvalue is trace, or you can use the product of the eigenvalue is determinant of the matrix. Choice on your side. So if I use the first property, sum of the eigenvalues 2 plus 8 plus lambda 3. What is the trace of the matrix? 6 plus 3 plus 3. So that implies lambda 3 is my 2. Fine. Or if you find determinants, then product of the eigenvalue is 2 into 8 into lambda 3. So that will be, if you find the determinant of the matrix, you will get answer is 32. You can find that determinant. Fine. So that means lambda 3 will be my again 2. So now if lambda 3 is my 2, the second eigenvalue is my third eigenvalue is my 1 over 2. So that is 1 over 2, 1 over 2 and 1 over 8 are the eigenvalues of the A inverse. Next one is if lambda is the eigenvalue of the matrix A, then K of lambda is the eigenvalue of the matrix KA. Again, we can start with the definitions. I can multiply both sides by scalar K. So what will happen? K of AX, which is equal to K times lambda X. So I can, because K is a scalar, I can write as a K of X, which is equal to K of lambda into X. Now if you again compare it with AX is equal to lambda X, lambda is the eigenvalues of the A. So in this case, K lambda is the eigenvalue of the KA, and that is the required proof of this result. K lambda is the eigenvalue of the KA. Similarly, the next property is if lambda is the eigenvalue of the A, lambda raised to power n is the eigenvalue of the A raised to power n. So by the definition, let's start with the A square. How you can find the A square? So I can pre-multiply both sides by A. So that will be A into AX, which is equal to A into lambda X. Fine. In this side, I can take a lambda is constant, or outside it is A of X. I can substitute the value of the AX again. So then lambda into lambda is lambda square X. And this side I can return as A square of X. What does it implies? Lambda square is the eigenvalue of A square. Fine. Lambda square is the eigenvalue of the A square. Similarly, I can pre-multiply this value by A. So it's a cube. I can return is A of lambda square X. Again, I can take a lambda square is outside. It is A of X. Again, I can substitute AX is lambda. It is lambda cube X. So therefore, lambda cube is the eigenvalue of the A cube, and so on. Similarly, you can find A4, A5, and in general A raised to power n. Lambda n is the eigenvalue of the A raised to power n. So look at the numerical example corresponding to these properties. If A, because A is my 2 cross 2, so that means it has a 2 eigenvalues which are given as 1 and 3. Fine. Then your target is to find the 2 of A. So by using the previous property, K of A has the eigenvalue K of lambda. So what is the meaning of that? Minus of 2 and 6 are the eigenvalues of the matrix 2A. Similarly, if somebody will ask you find if A has the eigenvalues 1, 3 and minus 2, can you find the eigenvalues of the A square? So we all know if A has eigenvalues lambda, then A raised to power n has the eigenvalues lambda raised to power n. So that means 1 square, 3 square, minus of 2 square. That means 1, 9 and 4 are the eigenvalue of the A square. Similarly, eigenvalues of the A raised to power 5 will be 1 raised to power 5, 3 raised to power 5, minus 2 raised to power 5. That are the answers of this problem. Okay, look at this next one. The eigenvalues of the idempotent matrix, that is A square is equal to A, are either 0 or 1. That is the meaning of this property. It's a very, very useful property. So let's start with this one. A has the eigenvalues. A is the idempotent matrix with the eigenvalue A square is equal to lambda. Fine. Now, my target is to start with the eigenvalues. So let's start with the, let lambda is the eigenvalues of the A, so that Ax is equal to lambda x. Fine. I can pre-multiply both sides by A. So it's a square of x. It is A into lambda x. I can take a lambda is outside. This number is my Ax. Fine. So that implies, what is the meaning of that? If we multiply, Ax will be lambda x. Fine, pre-multiply by A, that will be A square x is lambda of x, that is a lambda square x. A square, what is the value of the A square? By using equation number 1, A square is my Ax. Fine, and I can use the equation number 2 and 3. So this value is by using from 2 and 3. Fine. Now because again I can return this number is lambda minus lambda square of x is equal to 0, but x is my non-zero vector. So this implies lambda minus lambda square is 0, which implies 1 minus lambda is equal to 0. That means lambda are 0 or 1, because lambda is the eigenvalues of the A. Therefore, eigenvalues of the idempotent matrix is 0 or 1 always. Look at the next one. The eigenvalues of the two similar matrices are same. If I choose A and B are the two matrices, are the two similar matrices. Fine. What does it mean? By the linear transformation, I can write A is P inverse of BP, or I can write B is equal to P inverse of AP, where P is my invertible matrix. Fine. That's the meaning of this similar matrix. A and B are the similar matrix. That means I can write this value. Now the eigenvalues of the A, if I assume A has eigenvalue lambda, B has eigenvalue mu, then what is your target? Your target is to prove lambda and mu are both same. That's the meaning of this case. Fine. Or I can start with the A minus lambda I. By the definition, I can substitute the value of the A. I can write these quantities. I can write lambda of I is P inverse of lambda I into P. Why? Because lambda of I is my scalar. So I can take its outside. Fine. So that is a P inverse P is my identity. I can write identity is my P inverse P. Fine. So that means minus P inverse lambda of P. Now P of lambda of I. So that means P inverse is outside. B minus lambda I of P. I can write it easily. Fine. Now if you open this bracket, because determinant, I can write determinant of B minus lambda I, determinant of the P. These two values which comes to be the 1. Fine. So therefore, A minus lambda I and B minus lambda I determinants are same. Remember, what is the meaning of the A minus lambda I? That is called as the characteristics equation of the matrix A. B minus lambda I is the characteristics equation of the matrix B, and A is the eigenvalues of the lambda is the eigenvalue of the A. Here lambda is the eigenvalues of the B. So therefore you can see both the equation has the same characteristics polynomial, and whatever the roots of these polynomials are called as eigen's value. And once the characteristics polynomial are same, that means roots are same, and once the roots are same, that means the eigen's values are same. Next property is the eigenvalue of the Hermitian matrix are always real. That means whenever your matrix is A star, fine, or you can say A is A complex conjugate, transpose, then the lambda is always my real. It can never be complex number. Very, very simple. I can start with the definition of the Hermitian matrix. A is equal to A star. Fine. Now your target is to prove, if I say lambda is the eigenvalue of T, then by the definition Ax is equal to lambda x. Fine. I can pre-multiply both sides by A star. So it's a star of A is A star of lambda x. Fine. Lambda I can take as outside. So it will be, or I can pre-multiply by x star. Fine. Now this value lambda is outside. It will be x star of x. Now x star of x I can written as norm of the x square. Fine. Now you can see, because x is my non-zero, the right hand side is a non-zero provided lambda is a non-zero. But here lambda may be 0. Lambda may be 0. Now if I prove that, because in order to prove this number is real, I have to prove that x star of ax must be real. Fine. So what is the meaning? Once you are in the complex number, when you can say that z is a real, if you prove that z transpose is my z, fine, then it will be the real. Fine. So I can start with the star definitions. So it will be x star a x star of, fine, so that number will be x star a of x. Now you can see the complex conjugate, star is a complex conjugate of the Hermitian. So whenever any of the matrix, say b star of the b, what does it mean? That means the matrix x star ax is my real. So this value is my real, norm of x square is a real, therefore the lambda is my real. Hence, eigenvalues of the Hermitian matrix are always real. Eigenvalue of the Skew-Hermitian matrix is either 0 or purely imaginary numbers. That's the converse of the Hermitian matrix. Fine. So again, I can start with the similar properties. A is a Skew-Hermitian matrix. A is a Skew-Hermitian means A is equal to minus of A complex conjugate transpose. Fine. Now, I can multiply both sides by iota. Fine, then it's a iota x is iota lambda x. Is it fine? There is no issue. Now, whenever, what is the iota of a? If a is my Skew-Hermitian, if then iota of a is my Hermitian matrix. Fine, we all know if a is my Skew-Hermitians, then iota of a is always the Hermitians, and from this case we can say iota of lambda is the eigenvalue of iota a, but iota a is my Hermitian matrix, and once the Hermitian matrix, by the previous property, eigenvalues of the Hermitian matrix are always real. That means lambda of I should be real. So real means either, when it will be the real, either lambda is my 0 or lambda is a purely imaginary number. Because if lambda is say my 3, then it will be my 3 iota, that is not a real number. So when it will be the real, either lambda is a 0 or lambda is a purely imaginary number. For example, can you say whether the eigenvalues of the A are real or not? Again, I will tell you the two methods. The first method is by using the property. Second method is by using the calculations. Now, when it will be the real, if you prove that the matrix is Hermitian, then the eigenvalues are always real. Fine. So how you can prove the Hermitian? Our target is to prove this number. Fine. So let's firstly start with the A transpose. What is the A transpose? 2 iota minus iota 2. Fine. Oh sorry, इसे मैंने transpose कर दिया ना. हाँ, yes, A transpose will be, A complex conjugate will be, now you can say what is the transpose of this matrix, which is 2 minus iota, iota and 2, which is same as matrix A. Therefore, the matrix A is my Hermitian matrix. And once the matrix is Hermitian, by the properties, all these eigenvalues are real. Second method is I can find the eigenvalues of this matrix. A minus lambda I is 0. Fine. So I can say 2 minus lambda minus iota, iota 2 minus lambda is 0. So if you open this bracket, it is 4 plus lambda square minus 4 lambda minus minus plus and 1. So that will be lambda square minus 4 lambda plus 3 is equal to 0. Lambda will be 3 comma 1. So these are the eigens values of the matrix A. Now you can see 3 and 1 are the eigenvalues and both the numbers are my real. Okay, next one is the eigenvector. The eigenvectors are not always unique. Again, if I assume that lambda is the eigenvalue, then ax is equal to lambda x. Fine. Now I can choose any, say k is any real number. Fine. I can multiply both sides by k. So what does it mean? That means k of a x is equal to k lambda of x. Fine. Or you can say a into kx, which is equal to lambda times kx. What does it mean? Lambda is the eigenvalue of the a, and what is the meaning of the kx? Kx is the eigenvector of the matrix A. Fine. So now you can see k is my any non-zero real number. K may be 1, k may be half, k may be minus half, k may be 3 by 4. Fine. K may be 10, maybe 100, maybe 400 and so on. Now because kx is also the eigenvector, therefore eigenvectors are not always unique. Next one is the eigenvectors corresponding to the distinct eigenvalues of the real symmetric matrix are orthogonal. That means the eigenvectors corresponding to the distinct eigenvalues. If I assume A is my real symmetric matrix and they have the eigenvalues, lambda and mu are the eigens values. Fine. If I assume the eigenvector corresponding to lambda is x, y is the eigenvector corresponding to the eigenvalue mu, then this result say x transpose of y is my 0. That's the meaning of the orthogonal. Fine. That's the meaning of the orthogonal. So if I say x and y are the eigenvectors corresponding to the eigenvalue lambda and mu, that means ax is equal to lambda of x, ay of mu of y. Fine. That's the meaning. Mu is the eigenvalue of the a, y is the eigenvector. Lambda is the eigenvalue of the a, corresponding eigenvector x. Now your target is to prove x transpose, or you can x transpose of y is equal to 0. Now since we need a y transpose, so I can pre-multiply the equation number 1 by y transpose. Fine. So it will be y transpose of lambda x. Lambda is a constant which is outside. It's a y transpose of x. Or since we need x transpose also, so I can pre-multiply equation number 2 by x transpose. Fine. So I can pre-multiply equation number 2 by x transpose. A of y, mu I can take as outside, x transpose of y. Now if you look at that, I need a y transpose ax. So I can take an transpose on the both side. Fine. So now I can take an x transpose ay. I can take an transpose on the both side. Now you can see what will happen. This equation becomes y transpose a transpose x. This value becomes y transpose x transpose of x is x. Mu is a real number, so that is my mu. Now A is my symmetric matrix. That means A is equal to A transpose. I can use A transpose is my A, which is mu y transpose of x. If I write this is equation number 4, this is equation number 3. Now you can see the left hand side are same. This implies lambda into mu transpose of x, lambda of y transpose of x, which is equal to mu y transpose of x. Fine. That means lambda minus mu of y transpose of x is 0. Now you can see lambda and mu are my distinct. That means lambda is not equal to mu. This implies, what does it implies? This implies y transpose of x must be 0. Fine. Once the y transpose of x is 0, that means they are orthogonal to each other. Now, based on all these properties, we will see what are the eigenvectors of the AB, product of the matrix and the sum of the matrix. Make sure A and B have the different matrix. If I assume lambda is the eigenvalue of the matrix A, mu is the eigenvalue of the matrix B, can you say lambda of mu and lambda plus mu is the eigenvalues of the matrix AB and A plus B? एक बात याद रखो बच्चों, मैंने एक प्रॉपर्टी बताई है अभी आपको. इफ लैम्डा इज द आइगन वैल्यू ऑफ द ए, देन ए स्क्वायर हैज द आइगन वैल्यूज लैम्डा स्क्वायर. दैट इज you can see a square means a into a, that is eigen value of lambda into lambda. पर यहाँ पे क्या है, ये a और a सेम है, लेकिन यहाँ पे क्या है, a और b अलग अलग है. फाइन. So can you say this result is true? The answer is no. Answer is no. So let's see how you can check about the eigenvectors of the AB. So I can write this number is bx. I can substitute the value of the bx. Fine. Mu is my outside, that is my ax. I can substitute the value of the ax. If lambda is the eigenvalue of the a, that means ax is equal to lambda x. Mu is the eigenvalue of the b, that means bx is equal to mu of x. So that will be mu of lambda x. So you can see ab of x is equal to mu lambda of x. What you conclude? Mu of lambda is the eigenvalues of the AB. Fine. Or lambda of mu or mu of lambda, that's a scalar numbers. Fine, is the eigenvalue of the matrix A. But remember students, this proof is incorrect. This proof is incorrect. Can you think about why it happens so? The reason is, in this case, I assume x is the eigenvector of both A and B. Of both A and B, but they are not always true. The mistake is because we assume A and B have the same eigenvector x, but that is not always true. For example, I will tell you example. So that means lambda mu is not the eigenvalues of the AB. Similarly, you can prove that a lambda plus mu is not the eigenvalues of A plus B. ये सिर्फ इसीलिए हुआ है because A and B are the two different matrices. Fine. Now, for example, now can you find the eigenvalues of matrix A? Clearly say A has eigenvalues. ये तो diagonal matrix होगी ना, तो 0 and 0 are the eigenvalues. Similarly, what are the eigenvalues of the B? 0 and 0. So according to this result, what is the eigenvalues of the AB? ये भी 0 0 होना चाहिए. Fine. And A plus B के eigenvalues क्या होने चाहिए? 0 plus 0, 0 plus 0. ये होने चाहिए. But that is not true. Why? Can you find the value of the AB? And can you find the matrix A plus B? So what is the A plus B? 0, 1, 1, 0. Fine. Now clearly say what are the eigenvalues of the AB? Eigenvalues of the ABs are 1 and 0. Eigenvalues of the A plus B is my plus 1, minus 1. Clear? Now you can see how you can find. Again, you can see AB minus lambda I characteristics equation. Fine. Like I can solve for you 1 minus lambda 0, 0, minus lambda 0. Now if you solve them, you will get lambda is 0 and 1. Fine. But as per the definition, what will happen on the lambda mu? That's a 0 and 0. So that is not always true. So this result is not always true. But make sure this result is true only if AB is equal to BA. And if you look about this example, AB and BA are not same. Fine. So that's why they have not saved the eigen's value. Chaliye, look at this other one. Find the third eigenvalues of the matrix. So it is a 3 cross 3. You need to find the 3 eigenvalues. The first eigenvalue is 2. Second is third eigenvalue we need to find. Again, I can use the concept sum of the eigenvalues is trace of the matrix, or you may use as product of the eigenvalue is determinant of the matrix. So let's start with this sum of the eigenvalues 2 plus 8 plus third eigenvalue. What is that trace? Trace will be 6, 3 and 3. That is 12. So can you find the third eigenvalue? Third eigenvalue is my 2. And the same you can solve it either by the product of the eigenvalue. The product of the two eigenvalues of 3 cross 3 matrix. If A is my 3 cross 3, the product of the two eigenvalues. If I say there are the 3 eigenvalues, what is given that? The product of the two eigenvalue is my 16. Can you find the third eigenvalues? So now since in this case is the product of the eigenvalues, I can use the concept of the product of the eigen's value is equal to determinant. That implies 16 lambda 3. What is that determinant is? 6 into 9 minus 1 minus plus of 2. That will be minus of 6 plus of 2. And the third number is plus of 2 minus of 6. Now you can solve them. It's a 8. It's a 48. 4. 4 to your 8 minus of 4 minus 8. So that will be 40. 40 minus 8 is 32. 16 into lambda 3 is, so lambda 3 will be my 2 is the right. Fine. Look at one more example. Again, it's a 3 cross 3. So A has my 3 cross 3 matrix. The 3 and 15 are the two eigenvalues. Find the determinant of A without expanding the determinants. Without, that means you can never expand like this way. 21 minus 16 plus of 6. Fine. Plus of 2. 24 minus 14. इस तरह से नहीं करना आपको. Without expanding. Now because these are the eigenvalues, I can use the eigenvalue property. That means I can use the product of the eigenvalues is equal to determinants. That means 3, 15, lambda 3 is my determinants. So but the question is how we can find the lambda 3. Yes students, can anybody tell me how you can find the lambda 3? Yes, that's quite easy. I can use the property. Sum of the eigenvalue is my trace of the matrix. So what are the eigenvalues? One eigenvalue is 3, second is 15, third eigenvalue is lambda 3. So can you find the trace? Trace is my 8, 7 and 3. So if you add them, it is my 18. Third eigenvalue is my 0. Fine. And if you substitute here, what is the determinant? Determinant will be 0 is the right answer of the problem. So that means if you try to expand them, that will also give you 0 is the right answer. So these are the all way you can solve the properties with the help of the numerical example in a very, very simple manner. I will explain you the next lecture on the 20 plus numerical examples on the eigenvalues. Till then, you can follow my playlist Linear Algebra with all those previous lectures, and you can like and share on this video. You can share this video with your friends. Happy learning always. Best wishes to everyone. Thanks for the watching.